Okay, good afternoon. Let us start our lecture. So today we continue to discuss about hypothesis testing. So there are a few things that you have to know. So first of all is how to set up the hypothesis. So there are two options. One is called null hypothesis. So it's a statement, all right, concerned in statistics usually is concerned about certain characteristic of the population. For example, the population mean or the population variance. So a statement about the population mean or the population variance or the difference of the population means. All right. So the alternative is as the name alternative. So it's another statement that we can based on which we decide on our testing procedure. All right. So you given a problem, you have to know how to set up the hypothesis. All right. Then we'll talk about the level, significance level. So in order to know what significance level is, we need to distinguish between different types of error. So we have this type 1 and type 2 error. All right, so you have to know both. So what is type 1 error? Type 1 error basically is the error that we commit when the null hypothesis is true. So when we commit this type of error, because the null hypothesis is true and you do not, or you reject the null hypothesis. You don't believe in the null hypothesis, so you make a mistake. So that one is called type 1 error. So how likely we commit a type 1 error? So that translate means probability of type 1 error. All right. So we have this null hypothesis and the alternative hypothesis. To make it more concrete, let's say I want to have mu equal to 10 against, or equal to 100 and against mu does not equal to 100, for example. Oh, thank you. Yeah. You see, I only look at my screen, it's perfectly all right. I can see what I wrote. All right. Okay. So we have this hypothesis, and then we have this type 1 and type 2 error. So type 1 error is when H0 is true, and we do not think that is true, so we reject it. So that is a type 1 error. Type 2 error is when H1 is false, H0 is false, and then we do not reject it. We also commit an error. All right, so this is the error, types of error. Then we have this significance level. Usually we set a 5% or 1%. All right. So what is this significance level? It is the probability of committing a type 1 error. All right. So in other words, even now hypothesis is true, then based on our decision rule, we still reject it. But we want to control this error to a very small probability. So usually we set it at 5% or 1%. All right. Then you ask, then what is the probability of type 2 error? All right. We also want this to be small. All right. In fact, the ideal case is that both types of error has a very small probability. All right. We can achieve that by increase the sample size. But usually for fixed sample size, we cannot reduce both chance of committing both types of error. So we try to control the type 1 error chance. At the same time, we try to minimize this probability of committing a type 2 error. All right. And so there's this term called power of a test, which is equal to 1 minus this probability. So you can see that if the probability of committing a type 2 error is small, then the power is big. All right? So these are the terms that we are going to discuss. And finally, how do we make the decisions? So we are going to make a decision based on two approaches. One is called critical region approach. So the idea is similar to the confidence interval. So long as, for example, we look at this hypothesis, all right? So we decide that, okay, if x bar minus 100 over s over root n, if this is bigger than certain number, what is this number? The number may be t n minus 1, let's say 0.025. So this is our decision rule. Whenever I got a sample, I calculate x bar, calculate the sample variance, all right? And then I substitute in this formula, take the absolute value of this, and if I find out that this number from the sample of data is bigger than this number, then I make a decision. The decision is to reject it. Why reject it? Because this quantity suppose follow a t distribution with n minus 1 degrees of freedom. All right? So what I'm saying is that, okay, under the null hypothesis, this supposed to behave like that. All right? So I decide that, okay, if this quantity, the absolute of it, lies between these two numbers, t n minus 1, 0.025, or minus t n minus 1, 0.025. All right? So if it's false here, if after I got a sample, I compute this one, it falls here or falls here. All right? Outside this, bigger than this number, or the negative of this value is smaller than this negative of this number, then we make a decision. The decision is to reject the null hypothesis. So I believe mu may be not 100, maybe bigger than 100, or maybe smaller than 100, but it's not 100. The reason or the rationale is that if mu equal to 100, if mu is really 100, I get my sample from this population with mean equal to 100, all right? And then I calculate this x bar minus 100 over s over root n. This number should behave like a t distribution. But now what I see is quite extreme. Why I consider it extreme? Because it falls in the region for which the chance of greater than those numbers are very small. All right? If I get a sample, my value is somewhere here. I consider it is extreme, right? Because the chance that more extreme than this number must be less than 2.5%. Am I right? Because this area is 2.5%. So if you are here, then of course the chance is even smaller than 2.5%. So I consider it extreme. How about here? If I got something here, is it extreme? Yes, it's also considered extreme. It's extreme in the sense that it's very small. So maybe the mu, the actual mu, is not 100, but a number less than 100. All right, so this is called critical value, a critical region, which is defined by this critical value. This one we call it critical values. So the decision is based on a test statistics and based on the critical value. And we compare the test statistic with the critical value and then make the decision. Okay? Another approach is this p-value approach. This is more popular nowadays because we are able to compute this probability. In the old days, we don't have the resources to compute individual chance of calculate this p-value. So we just compare with certain fixed values. Okay, so what is the p-value? P-value is basically the chance that your test statistics, in this case, this is our test statistics, in this example, in this example, we're talking about this. All right, so this one, bigger than what you observed, or let's say, let me call this a t random variable with n minus 1 degrees of freedom, bigger than what you observe. This t observed is basically the x bar minus 100 over s over root n. But the x bar and the s, now we we calculate based on the sample. Or I can say that it's a realization of the random variable x bar and s. All right? I hope you not confuse these two things. This one with capital letters. So this is a random variable. All right? So x bar is the sample mean and s is the sample standard deviation. It's a random variable. And this random variable behaves like a t distribution with n-1 degrees of freedom. All right? Now, if I really take a sample and I have the values of this sample, just like tossing, I keep repeating this one, tossing a coin. Before I toss it, I know the outcome is head or tail. So the outcome is a random variable because you don't know whether it's head or tail. And the head chance is half, tail chance is half. But once you toss it, look at it, then you have the outcome. It's a head. So there is a realization of the random variable. So the same here. You look at the sample and you measure everyone, and then you got the values and you take the average of all this, you got the x bar realization. And similarly for the s. So you can calculate a value. So that one I call it t observed t value. That is from your sample. All right? So the observed value is a number coming from the sample that you have the value or the data. While when I talk about x bar minus 100 over s over root n with capital letter, those are random variables. Okay? So the p-value is how, okay, what's the chance? P-value is a little bit more complicated for two-sided. So we look at this quantity and this quantity, or a t distribution, n-1, which means this less than minus t observed. Oh, sorry, no minus. Just look at these two. So in other words, I'm looking at two probability. One is the t distribution greater than what you observed. So in other words, okay, what I'm saying is like this. So this is a t distribution with n-1 degrees of freedom. I take a sample, let's say a size of 30, for example. All right, so this becomes T29. All right. So then I calculate all this. So this is my observed value. Okay, to make it more concrete, let's say after I compute x bar, compute s, I got this value equal to, let's say, 2.5. 2.5. All right. So is this extreme? So we will look at this probability. That is this one. Is this also considered as another? It's also considered as extreme. All right. So what I'm trying to say is that we have to consider both sides, and then we take the minimum of the two. All right. So what happens if your observed value is somewhere here? If you every time you just look at how likely it is bigger than what you observe, then this is wrong. Okay? Let me repeat it. Your observed value can be close to the right-hand side. Yeah. Right? Then extreme means that it's bigger than it. Then it's extreme. But the value can be on the other side of extrema. Right? So when you consider, when you get the t observed t value, so you have to consider the chance of greater than it and less than it. All right. So let me ask you, same thing. If you earn $1 million, all right, are you rich? So you have to compare. Right, you think, are you rich, right? So you have to already know the direction. You compare how likely other people earning more than you do, right? But you can also, 1 million, in fact, right, maybe very poor, right? So you also have to look at what is the chance that someone earns less than you do, right? That is to answer the question whether you are poor or not. All right? Because we have two sides. We don't know whether we're talking about rich or poor. That's why we have to consider both sides. But now you have these two probabilities. So how to make a decision? We take the minimum of the two, right? So if I earn $1 million, I know that only 10% of people earning more than 1 million, and 90% earning less than 1 million. So I take the minimum of the two, then I know that, okay, I am rich because I'm on the top 10 percentile. On the other hand, if I earn 1 million, the chance of earning more than me is 90%, and earning less than me is 10%. So in that case, I'm poor because I'm on the bottom 10. So I have to choose the one with the minimum probability. Bigger than it, less than it, take the minimum one, all right, and multiply by 2. That is the p-value. Multiply by 2, you need two sides, you have to multiply by 2. All right? In order to be consistent with the inference from the critical value region, critical region approach. So that's basically about it. Then how to get these test statistics. So just like our chapter 6, under the conditions, whether it's normally distributed, whether you know some of the parameters or not, whether the sample size is big or not, basically it's similar to what we discussed in chapter 6. Okay, so now, too long the overview, right? So let's do some concrete thing. Okay, so hypothesis. Now an alternative hypothesis. So a statistical hypothesis is a statement, assertion, or conjecture. So basically, a conjecture is still a statement, but I don't know whether it's true or not. All right? So just like if I say A plus B equal to 1, so this is a statement. A plus B equal to 1. It can be true, it can be false, right? So it's a statement with true values. And of course, in statistical hypothesis, the statement cannot be just A plus B equal to 1. The statement should be concerned about the population, one or more population, or certain characteristics of this population. And to make life easier, we only consider two characteristics: mean and variance, all right, of a population, or the difference of the means, or the ratio of the variances. So these are the characteristics that we discussed in this chapter, all right. Others characteristics are not covered, all right. Okay, so here we use accept and reject, but in fact, I will prefer to use do not reject. Although in English, I think accept and do not reject are the same thing, but I told you, okay, think of it as a statement. So if I cannot I have no evidence to support it. I mean, I don't have evidence to reject it. So I will take this statement for the time being. But next time, maybe in the future, I may got some evidence, and then I will reject it. All right. I think I mentioned before. Suppose I go to the park, and then I say that there's no bird in the park, right? So the time that I go there, I don't see any bird, so the statement is right at that point of time. Then I conclude that I do not reject the statement. So in other words, I will not say no to this statement. But maybe the next day, when I go there, I see one bird there. Then I know that this statement is wrong, it's false. All right? So when I go there, there's no bird, I just say that I do not reject the statement. All right? It does not mean that the statement is true. At least I don't have evidence to say otherwise. So when I say accept, it means that I don't reject it. All right, I cannot say it's wrong, and it's based on the evidence that I have at that point of time. That I have no strong evidence to say that to reject it. All right. So reject means that this is my conclusion or my decision. I say that the statement is false. All right. So at that point, when I reject it, all right. So it simply means that at that point, I believe, I make a decision that, all right, that this statement is false. All right. Then if I say I accept it, it simply means that I don't have enough evidence to say that this is not true. All right. So at the moment, I just still keep using it. So that's why the status quo is the statement that we used with the null hypothesis. All right. So the null hypothesis, or the hypothesis that we say, is the one that we want to reject. All right. So remember I talked about I have a new drug. I want to say that this is better than the existing one. So I won't, okay, how do I measure this is better? So usually we look at the probability or the proportion of recover, right? So if the existing drugs in the market, the recovery rate is 0.8. So my new drug must have a better one. That's why I believe that. So if I set my hypothesis as the proportion or the probability of recovery is greater than 0.8, then what to do? This is not the right hypothesis that we want to reject. What we want to reject is that this P is not 0.8. All right? We want to reject this statement. What I'm trying to say is that for my new drug, P is the proportion of recovery for the new drug. All right? I believe the new drug should have a better probability, better chance of recovery. All right? But if I put it as the null hypothesis, the whole framework of hypothesis testing is trying to look for evidence to reject the null hypothesis. So, you believe it, why bother to look for evidence that this probability of recovery is bigger than 0.8? I don't want to look for evidence. All right. But on the other hand, I want to reject this statement of P equal to 0.8. All right. So that I get that information and that I make a conclusion, I make a decision that I reject the null hypothesis and I favor to the alternative. So that's what I try to look for. Okay. So always remember, the null hypothesis is the statement that you want to reject, or the status quo. So we believe everything remains the same and something new. So I want to reject the old stuff, reject the status quo, and favor to the new stuff. So the status quo will be set as the null hypothesis. So in this case, the status quo is that your drug is similar to the other drugs. So the probability of recovery should be the same. What we try to do is to say that I will not believe that there should be the P for this new drug should be different from 0.8. In fact, I believe it's bigger than 0.8. So I try to look for evidence to say that the P is bigger than 0.8. So my null hypothesis is the status quo, the old belief, or the one that I want to reject. All right. Okay. So the null hypothesis concerning a population parameter. All right. And usually, to make it simple, the null hypothesis, we always put it as equal to certain values. While the alternative All right. So for example, mu equal to 100. So that is an example of null hypothesis equal. So the alternative, we can have this one, or we can have this one. Do we have other choices besides these two? Not equal, all right? Not equal. Not equal means this the same as mu greater than 100 and mu less than 100. All right? When we say mu not equal to 100, so it can be bigger than 100, can be smaller than 100. But the null hypothesis, we try to make it equal. The statement is equal. Okay, so the alternative, we call it H1. So H1 can be more than one values. Can it be like that? Nothing wrong, all right? But of course, you can still test this one. In other words, you make a decision to whether you reject the null hypothesis or do not reject the null hypothesis. When you consider whether you reject the null hypothesis or not, there's a part that you have to make use of the information in your alternative. All right. In other words, different alternative may give you slightly different ways of doing things, or the test procedures is slightly different. All right. In other words, these three alternative will give you slightly different procedures. The test statistic may be the same, but the critical values are different. All right. Then when the fourth one that I just wrote down, the H1 is just mu equal to 110. All right. So that one we can also define as test statistics. All right. And basically, the test statistic will be similar to this one, because this is just a statement in here. All right. But you can test something like that. But then if you test something like that, then I will ask, okay, can you test for me mu equal 100 against H1 mu equal to 105? Do another one. So why just take this one? Any mu values that is bigger than 100, bigger than this, all right, as my alternative. So this is usually the case, one side test and two side test. Two side, why two side? Because it can be bigger than 100, can be less than 100. So we consider both sides. Okay, here's an example to illustrate the whole idea behind the hypothesis testing. So I have this population, and this population is very small. It's a certain school, the students' population in a particular school, and the IQ. We're looking at the IQ. So IQ is a random variable because each one have a different IQ, right? Different individuals, different students have different IQs. All right, so we believe that the population average is 100 for this school. All right. Theoretically speaking, this mu is equal to 100, right? For all the population, whether it is this school. I cannot say that. Okay. At first, I thought I want to say a university's IQ is also 100, but obviously this may be wrong. Right? Since you make it to university, your IQ may be slightly higher than the average. 100 is supposed to be the population. But on the other hand, I forgot about this. IQ is supposed to depend on your age also, right? When this quotient is compared with the same age group, right? Anyway, it's this psychology thing is not us. But let's assume that we are measuring the IQ, and this particular population we have this mu equal to 100. That means the average IQ of all the students in this school is 100. That's the statement. And we believe that maybe this school, the students there are very smart. Then my alternative is that, okay, the average may be greater than 100. Maybe this school is a special school, then maybe the IQ may be smaller than 100. But if we don't know whether this school is, whether it is this independent schools or a special school for special students, then that means we don't know which direction to go. So the safest is to include both. So in that case, we have mu that's not equal to 0. So for the tutorial question or for exam, you have to read carefully what is the alternative, what you want to find out. All right, whether it's bigger or smaller. If it does not indicate the direction, whether it's bigger or smaller, then we take the safe route, not equal. That means include both. All right? Okay, so this is called two-side alternative. And the other one, these are called one side. All right? This is another one side. So these are one side alternative. So a one side alternative, we use a one side test procedure. All right, here is the example to illustrate. So we have this population. All right. What is this? Yeah. So this is the claim. The population mean IQ. Please make sure that you remember is the statement is concerning about the population. So it's not a random variable. It is fixed. All right. So here the statement is that the population mean is 100. Population mean IQ is 100. All right. So we select a sample. I have to stress it's a random sample. So now we have a sample, a subset of the population. And based on this one, calculate the sample mean is 70. Then, do you believe that the mu is 100? All right. So, our decision will base on this. Whether it's likely to see something. Okay. In other words, if mu equal to 100, condition of mu equal to 100, how likely you see something like that? Is it correct? No. X bar equal to some value is not an extreme. Just like, right? Suppose your exam marks is from 0 to 100, right? So it got 95. So suppose if it's random, the chance, okay, maybe not exam marks. So suppose I have 100 numbers, 1 to 100. All right? I take one number. So the outcome, no matter what outcome it is, it's supposed to be uniform. So it's 1 over 100 chance of getting a particular number. So the chance of getting a 1 and the chance of getting 100 are equal chance. All right? Then, so if I pick a number 95, so does it mean that my number is extreme large? So to answer that question, we look at what is the chance that you can get a number more extreme or bigger than 95, greater or equal to 95. The chance is only 6 over 100, right? So therefore, it's very unlikely, just like toss a die, 1, 2, 3, 4, 5, 6, right? 1 and 6 have equal chance. At least, I don't know whether, I like to have 6, right? 6 feeling that you have a bigger number, right? So you feel more. 5 also not so bad, right? Getting a 1, terrible, so small a number. But they're equally likely. Why you think that getting a 1 and getting a 6 is different? Because we believe that towards the large number. So we ask the chance that you're getting a number bigger than what I get. So if I got a 5, right? So I ask, is 5 a big number? So I ask, how likely that you got a number bigger than or equal to 5? And the chance is 2 over 6, 1/3, right? But if you got a 1, then you ask yourself, how likely you got a number bigger or equal to 1? The chance is 1. So that means what you have is very, very likely. So it's not that large. So the idea is like this. So how likely is it? All right? So it should be, okay, strictly speaking, it should be two sides. I mean, how likely it is bigger or equal to 70, or how likely x bar is less or equal to 70. And take the minimum of these two probability. So bigger than 70 is to check whether 70 is a large extreme. Less than 70 is to check whether this 70 is a small extreme values. All right? Extreme can be large, can be big, can be large, can be small extreme, right? So, but basically we just ask this question: how likely it is? If it's unlikely, then we believe that this population may have a mean IQ which is not 100, but smaller than 100, lower than 100. All right. Okay. This is a graph to show that. Okay, so this is how X bar behaves. That means you take many, many samples, and then the sample mean will behave like this. Okay. What is this point? This is where you expect X bar should be. So what is it? So it's mu. This is mu. All right. All right. So under the null hypothesis, I have to stress, under the null hypothesis, this is equal to 100. Now I see 70 here. So is it extreme? Is it likely that you will get a sample such that the sample mean is equal to 70? So we look at it. The chance less than it is very small. Of course, greater than it is very large. All right. But since it's less than it is so small, so this 70 is extreme. It's extreme. Right? So, okay, hypothesis is this one. So if this is true, then how likely we have? So if it's unlikely, then we reject the null hypothesis. Now if you draw a sample, all right, and then you check the value X bar. So if X bar, let's say, is 95, all right, then if it's here, then if mu is 100, it's likely that you will see X bar 95, because the chance greater or equal to 95, X bar greater or equal to 95, or X bar less or equal to 95 is quite big. This probability is quite big. Of course, this is also big, but when we look at the minimum of these two, so it's quite big. So 95 is okay. So in other words, our underlying assumption that mu equal 100 is fine. That's why we see a sample. We got a sample which gives us X bar equal 95. But if you get a sample with a mean equal to 70, then it's no good, because the chance of getting 70 is small. Although I did not elaborate how to get all this, but the idea is that if it's unlikely to see what you see, all right, unlikely can be both sides. So that's why for two-side alternative, you have to consider both probabilities and take the minimum. Okay, so this is the type 1, type 2 error that we have been discussed this twice. State of nature, H not true. Then you reject it. Sorry, you make a mistake. So this mistake is called type 1 error. Then if H naught is false, you reject it. Okay, this is nice. You did not make a mistake. But if H naught is true, you do not reject H naught. Yes, you make a right decision. But if H naught is false and you do not reject it, you make a mistake. And this mistake, we call it type 2. All right? Okay, then we would like to know how likely we commit a type 1 error. So the probability of committing a type 1 error. When we commit a type 1 error, we make a decision when the null hypothesis is true, and the decision is to reject H naught. So we commit a type 1 error. So the chance of doing this is equal to alpha. Alpha is just a number, okay? And then when we commit type 2 error, this is the chance committing a type 2 error, which means that you do not reject H naught. Given the H naught is false, then you reject it. But, okay, so this is a little bit vague. When I say H naught is false, to calculate this probability, even that H naught is false, is not that easy. So usually we specify a particular value of this parameter, which is under the null hypothesis, under the alternative hypothesis. So if the alternative hypothesis mu does not equal to 100, then I can only compute this probability, all right, with mu equal to any number except 100. I can consider 105, all right, or consider mu equal to 92. So all these numbers are different from 100. So I can calculate the probability of do not reject H naught when mu equal to 105, which is part of the alternative, or mu equal to 92, which is also part of the alternative. My point is that I cannot compute the probability. I cannot compute this probability of do not reject H naught, given mu not equal to 100. I cannot compute this probability. Why I cannot compute this probability? Because, okay, it's very simple. Let me decide that, okay, if X bar is less than 70, I will reject it. Can we compute this probability? Can we compute this probability? We cannot. Why I cannot? Because in order to compute this probability, what is the random variable involved? X bar. Then ask yourself, what is the distribution of X bar? It's normal. If the underlying distribution is normal. So it's normal. What's the mean? Mu. And what's variance? Sigma square over n. Suppose sigma square is known. All right. But do you know mu? No, because I say that mu is that's not equal to 100. So it can be any number. So how to compute an infinite number of possible distribution. So X bar may follow normal with 99 mean and variance sigma square over n. X bar can be normal with mean mu equal to 98. So many of them. So I cannot compute this probability. So that's why I need to specify a value, mu, which is not 100, which is a member of the alternative hypothesis in order to compute the probability. All right? So although the statement says that the null hypothesis is false, but in order to compute this probability, I need to specify the value of mu, which belongs to the alternative hypothesis. Okay. So this is type 1 error, rejecting H naught when H naught is true. All right. Not rejecting H naught when H naught is false. That's type 2 error. And the probability of committing a type 1 error is called level of significance. Right. You may heard about it. So it usually is set at 5%. So in other words, test procedure, what we're going to do to make the decision, based on which we make the decision, is something to do with this level of significance. We have to set this one. In other words, we try to control the chance of committing a type 1 error. Usually we control at 5%. Sometimes we control it at 1%. So that means my test procedure is to make sure that the chance of committing a type 1 error, that means reject wrongly the null hypothesis. When the null hypothesis is true, the chance is about alpha, 5% or 1%. All right. I can make a decision, all right, without committing a type 1 error. All right. So no matter what I see in the sample, my decision is that I do not reject the null hypothesis. Then I won't make any mistakes. Am I right? Right? So let's go back to the example. Mu equal 100 is the null hypothesis. So I take a sample, calculate x bar. You set x bar equal to 70. So you make decision. So I said 70. My decision is I do not reject the null hypothesis. So even the sample mean is equal to 30, I do not reject the null hypothesis. If the x bar equal to 1000, I do not reject the null hypothesis. I won't commit any type 1 error. That means if the mu is 100, because my decision is I do not reject it, I won't commit a type 1 error. Wow, so it's good, right? But then I commit a type 2 error with a very high chance. Because if mu is different from 100, I do not reject the null hypothesis, so I commit a mistake. I make a mistake. So I have to balance between these two, and usually we just control the type 1 error. So that's why most of the time the level of significance is specified. All right? And we have to set this in advance. Okay? What it means is that I have to state this one without looking at the data, without doing any statistical analysis. All right? So in other words, like kicking soccer, right? So the goalposts are there. All right? I kick the ball, try to get through the goalpost. All right? You can shift your goalpost to fit where your ball lands. Then it's cheating, right? So the same apply here. I set my level of significance at certain value. All right? Then I start doing all this analysis, and then the decision is based on that. All right? I will not make the decision by looking at the data first, do the analysis. Oh, it comes out that this. Okay, what I mean is that I'm trying to do. Okay, I'm saying that, okay, I will reject if it falls here and here. All right? So that is before I look at the data. So now I get the data and I calculate. It falls here, I reject. It falls here, I do not reject. All right? So that's the idea. So now, okay, I did not draw the mark first. Then, okay, if it's here, after I got the data, okay, now I set my level of significance. Set it like here, so that this is where I reject it. So your what you see is fall in my region, so my decision is to reject it. So that's not right. All right? So what I'm saying is that you should set these marks first, then look at where your sample data will give you a test statistic. If it's lands here, reject. Lands here, do not reject. But if you don't set it, and then your data is here, false here, the test statistic. Oh, now I set my post. I want to reject it, so I set it here. Sorry, your observed value fall in my critical region, I reject it. If I don't want to reject it, so I set it here. Your data, your value, observed value, does not fall in my critical region, so I do not reject it. So that's not right. All right? So that's why you need to make it in advance. Usually 5%, 1%. So type 2 error, probability is beta. 1 minus beta is the power of the test. All right? Okay, here's a picture. Now this time I look at only two mu values. One is mu equal mu naught is my null hypothesis. Mu equal mu 1 is my alternative. All right? So now this is mu equal mu naught. All right? So if I decide that whenever the test statistics, this one, okay, for this type of problem is x bar minus mu naught, let's say over sigma over root n. All right? Standard normal. Assume sigma known. So if I got a sample and the value is here. This one, let's say it is, did I put it here? Alpha. So this is Z alpha. All right. So that this is standard normal. The chance of greater than this number is alpha. So this is Z alpha. So if alpha is 2.5%, if this is 2.5%, then this number is 1.96. All right. So in other words, I get a sample, calculate X bar. Suppose sigma is known, and mu naught is also known because it's under the null hypothesis. So I take the value in the null hypothesis, and then calculate it. If it's bigger than 1.96, I reject the null hypothesis. If it's less than 1.96, all right, I do not reject it. Even if I get the Z equal to minus 3. Where's minus 3? Minus 3. Oh, I'm sorry, this should be a different scale now. Anyway, okay, so if it's somewhere here, very, very small number, minus 3. If minus 3 is not small enough, minus 10, I still do not reject the null hypothesis because my alternative is mu1 where mu1 is bigger than mu naught. This is going to be the mu1 here. All right. So I do not reject the null hypothesis. Only those will give here, then I make a decision reject the null hypothesis. So do not reject null hypothesis. The probability is this area up to this point. That's 1 minus alpha, and this part is alpha. All right, so what is the chance of committing a type 1 error? Because I will make a decision to reject the null hypothesis, only this part. And the chance that the sample will give a value belong to this part is only alpha. So the type 1 error probability is alpha. All right? Now, what happens if mu is not equal to mu naught, but equal to mu1? So now, I should have an eraser to erase this pink curve and erase everything. But I still have this decision rule. Whenever I'm bigger than this value, I reject the null hypothesis. So now if mu1 is here, all right, x0 is false, and in fact mu equal to mu1 is here. So now you can see how likely I will reject the null hypothesis. What is the probability that I will reject the null hypothesis? If mu equal to mu1. Wow. It's not alpha, it's this part. All right? So the chance is very big to reject the null hypothesis. And this is the power. All right? And what is the probability of committing a type 2 error? Type 2 error is when you do not reject the null hypothesis. When the null hypothesis is false. In this case, when we say false, it means mu equal mu1. So in other words, whenever it is here, we do not reject, and that will commit the error, type 2 error. So this is the probability. Committing a type 2 error. All right? So that's why this part is 1 minus beta, and this part is beta. So this is a very simple graph to illustrate all this type 1, type 2 error. All right. So first of all, you have this distribution under the null hypothesis, which is mu equal mu naught, and then you look at the probability, which is alpha, which is 1 minus alpha. Oh, the first thing is to decide upon such that your decision is to reject the null hypothesis. Another part is you do not reject the null hypothesis. All right? Then you have alpha, you have 1 minus alpha. Next, we consider a different distribution. This time, the mu is under the alternative. In this case, it's the blue color. But your rule is still the same. When you reject or do not reject, it's still the same. Because you don't know whether mu equal mu naught or mu equal mu1. But let's assume that mu equal mu1. Then what's the chance that you reject? The chance becomes this area. The area that I wrote down. So this is 1 minus beta. All right. So this part is beta. So that's how all these are related. So to make the decision, we need a suitable test statistics. And the test statistic we have already discussed in chapter 6. All right. What we need is to specify alpha. In chapter 6, we need to specify in hypothesis testing, we need to specify the significance level. In chapter 6, we need to specify what? We have this 1 minus alpha, right? What do we call this 1 minus alpha in chapter 6? Is the level of confidence, right? All right. And you notice that one we use alpha, the other we use 1 minus alpha. All right. The bigger the confidence that you have, all right, the chance of committing a type 1 error is also small. Because think of it, if my confidence interval is from minus infinity to infinity, I will cover the true values. So it's the same as saying that I do not reject the null hypothesis. So that's why they are sort of equivalent. All right. So the decision rule can be found to divide set of all possible values of the test statistic into two parts, into two regions. All right. So one is called rejection region, or sometimes referred to as critical region. So they're the same thing. That means I divide it. Okay, I say two regions, but basically the region may be disconnected. All right. So I may have, okay, this is the test statistics. So this may be my rejection regions. So these two parts together are my rejection regions. And this one is my acceptance regions. So there are, in fact, 3 parts. But then 2 parts are considered as the rejection regions or critical regions. So when I say 2 regions, it means that there are 2, identified as two parts. But they may be disconnect. All right, so like here, this is rejection region, this is also rejection region. So the rejection region consists of the union of these 2 parts, while the acceptance region is just this part. All right. Okay. So once a sample is taken, so we compute the value of the test statistics. All right. If the test statistics fall in the rejection regions, so we make a decision. We reject the null hypothesis. If it falls in the acceptance region, we do not reject the null hypothesis. All right. So usually the region is decided by something called critical values. So remember, if this is my critical regions, so these are called critical value. Critical value. All right? That means I want to define my region by only specify the value. That is good enough. Specify the value to specify the critical region. So you just check whether your test statistics, the observed test statistics, falls in the rejection regions. Oh, what is this? Okay, I'm sorry that this one, the animation is terrible. Okay, so suppose I want to test mu equals 3 against mu does not equal 3. This is a two-side alternative. So we use a two-tail test. So it's like this. This is the, all right, so this is the behavior of the test statistics. All right, the test statistics. Suppose this describes the test statistics distribution. All right, so it's centered as 0. So I will set these 2 as the critical region, these 2 parts. All right. So I get a sample, calculate the test statistic value. So I got the observed test statistic value. If it's false here or false here, this region or this region, I will make the decision to reject the null hypothesis. All right. So So this part is our acceptance regions. Acceptance region. Usually we specify the rejection region. Now, if it's one side alternative like this, mu bigger than 3, then what is the critical region or rejection region? Think of it. If the alternative is true, you expect the mu should be big. If mu is, what can you say about x bar? Should be big, right? X bar should reflect the value of mu. So if mu equal to 100, you expect your x bar somewhere around 100. So in other words, you are only looking at the upper end of the distribution. All right, so the critical region now becomes this part. All right. Then if you're looking at alternative mu less than 3, so if mu is small, I expect my observed value should be small. So that's why I look for small values. So that's why the critical region is on the lower end. So this is my critical region. Look for small value for the test statistics. If this happens, I reject the null hypothesis. How small is small? I compare with this. This is the critical value. All right? Okay. Here is an example. Suppose I have this certain type of cold vaccine, okay, and it's only effective after 2 years. The effective rate go down to 25%. All right. So, in order to determine if a new and somewhat more expensive vaccine is superior, now this is the existing one. So now I have a new one, a new vaccine, and I want to check whether it's superior. All right, provide against the same virus for a longer period of time. So in other words, we expect, as this as a reference point, it should be better than 25%. All right? Okay. Let me, first of all, P is the, okay, it's saying 25%. So P is the effective, all right? So in other words, you can think of it, if applied to a group of people, patients or individuals, then after 2 years, only 1/4 of them is still have the protection from this vaccine. All right? So this is the statement. But now I have a new vaccine. So I want it to be more superior. And to measure superior means that you should have a higher proportion of patients that still got protected. So this is what we want. All right, this is something, we want to reject this one. This is a status code, and I want to change it to P greater than 0.25. Why is it greater? Because we believe that this new, this P, referring to the how effective this new vaccine, this new expensive vaccines, effective, percentage of effective after 2 years. So if it's the same as the existing one, so P should be equal to 25%. But if it's worse, then that means P should be less than 0.25 after 2 years. But now we are asking whether it's better. So the alternative should be P greater than 0.25. All right? So this is my H0, and this is my H1. This P referring to the how effective this new vaccines, all right, after 2 years. So give you 25% of the people get protected. This is F for other vaccines as well. But we want to find out whether it's really changed to a higher proportion of, or the proportion of percentage of effectiveness. That means more people get protected. Not just 1 out of 4, but maybe higher than that proportion. All right. This P referring to the proportion of effectiveness or the effective after 2 years. That means the proportion of individuals that are protected after 2 years. And we claim that it's better, so we put it as alternative. So now, we have 20 patients or 20 people, choose random and inoculate with this new vaccine. So this is our decision rule. This is our decision rule. If more than 8 of those receiving the new vaccine surpass 2 years period without contracting the virus, that means if more than 8, not including 8, more than 8 got protected after 2 years, out of 20, right? Then we consider that this new vaccine is really better, in the sense that the proportion of the population protected from this virus is higher than 1/4. All right. So the decision rule is based on X, where X is the number of individuals or number of persons out of 20, right? We have 20 that surpass the 2-year period, all right, without contracting the disease. This is considered as a success when you do not get this virus last more than 2 years without contracting the disease. So it's considered success. Okay, 8 out of 20 are successes. More than 8 successes out of this 20. Then we'll consider the vaccine is better. All right. So this is equivalent to test the null hypothesis and the alternative hypothesis. All right. And X is a random variable. Our decision is based on the random variable X. X is the number of people protected after 2 years. So if X is 9 or 10 or 11 up to 20, then we believe that the vaccine is better, have a better P, a higher P. All right. But if the number of persons protected is 8 or less, then that means this is as good as the others. All right. You may think, why I not choose 1/4, right? What is 20? 1/4 of 20, 5, right? So why don't I choose when it's 1, 0, 1, 2, 3, 4, 5? I accept it. And if it's like that, then I reject it. Is it good? You see, you just look at the mean. The mean is 5 because it's 1/4 of the 20 or 5. So it's not reasonable to make such assumption. To make such decision. Right? You're just less than the mean or greater than the mean. So it's likely to be half-half, but of course not exactly half. But anyway, this is for this particular problem. This is our decision. All right. So now I would like to know, based on this, to compute the type 1 error probability and the type 2 error probability. All right. Now I told you my decision rule is that when this number of individuals out of this 20, they do not contract the disease within 2 years, consider success. And if the number of successes is 9, 10, and so on, up to 20, then I will make the decision, reject the null hypothesis. But if it is 0 to 8, I do not reject it. So I ask, what is the probability of type 1 error? All right. So we want to calculate the probability of getting type 1 error. So it means rejecting H0. So this is all definition, reject H0. So when do we reject H0? So we reject X naught when X is bigger than 8. When X is bigger than 8. So we reject the null hypothesis. Under the null hypothesis, so under the null hypothesis, P equal to 1/4. All right, so just calculate this probability. Then you ask yourself, what is the distribution of X? What is its distribution? So that's why we need to learn from chapter 1 up to chapter 4, right? So X is the number of success out of 20 trials. So it's a binomial with 20. And what is P? We say that the probability of success is 1/4. All right, so this means that you calculate X bigger than 8 if X follow a binomial distribution with n equal 20 and probability of success is 1/4. So we just use your probability, this may be in your statistics tables. If not, it should be given there. All right, so to calculate this probability, or use a graphic calculator, right? Okay, I believe you don't have to calculate how many terms are 12 terms here. Each has a product of this, and one involved combinatorics. It's very tedious. All right, so we will not be asked to compute all this so tedious computation. All right, so the statistics table should be specially designed to give you the answer. You can read out from the statistics table. I think you can read out from the statistics table. I think the statistics tables that I provide with n equal to 20. Okay, so it's 0.0409. So what does it mean? It means that the chance of committing a type 1 error, that means the chance of rejecting the null hypothesis wrongly, is only about 4%, based on this decision rule. So it's not that bad. All right. On the other hand, we will also like to ask, all right, so what happens? What happens of getting the probability of committing a type 2 error? So we cannot answer this question unless we specify the P. We cannot say probability of do not reject. Do not reject means X less or equal to 8, given that P is greater than 1/4. All right? X less or equal to P, the decision is to do not reject the null hypothesis. Right? This is do not reject the null hypothesis if P is greater than 1/4. So as I told you just now, what is the distribution of X? X is binomial with n equal 20 and with P. So this P here, so many possible P. So that means there's so many probability distributions. So you cannot compute. So the only way that we can do is to specify the P, which is one of the values in the alternative. So we specify P, let's say P equal to 1/2. Okay? This is just a particular value. Why I choose that? So it just belongs to the alternative hypothesis. You can try P equal to 1/3. All right? So you just calculate this probability of X less or equal to 8, which means that you do not reject the null hypothesis when P equal to 1/2. All right? So the answer is 0.25. So what does it mean? It means that based on this decision rule, if P is half, then the chance of committing an error is 0.25. So in other words, what is the chance that you will reject the null hypothesis? So the chance of rejecting the null hypothesis will be 1 minus beta. this is the chance of committing an error. The chance of not committing this error, that means you reject the null hypothesis. If P equal to 1/2, what is the chance? The chance is equal to 1 minus 0.2517 or 0.7483. So it's very good. When P is very far away from 1/4, it's 1/2, all right? Then my decision rule achieves two things. The chance of committing type 1 error is about 4%. The chance of rejecting the null hypothesis when it is false, or when P equal to 1/2, is about 0.74, about 75%. Right? So the decision rule seems okay. All right? Okay. So now, the rest of the chapter, we'll just implement what we just discussed in the previous section, all right? And combining with what we learned in chapter 6. Okay, so now, the first test, a null hypothesis concerning about the mean, mu, all right? And with known variance, all right? Okay, so this scenario, remember there are three things, right? Whether it's normal populations, what's the second one? Whether other parameters are known or not. Here we are talking about statement concerning about mu. So the other statement is about no. We basically, yeah, okay. So sigma square is known. And the third one, you may need it or you may not need it, is whether the sample size is large. All right. So you have to consider these three different criteria. So here we say that if sigma square is known, all right, so this is yes. All right. If the underlying distribution is normal, yes. Then it doesn't matter whether your sample size is big or not. All right. And even if this is no, but then if this is big, all right, then we can apply the central limit theorem and still able to do it. All right. So the test statistic will be like this. We are in mu. So naturally, we look at X bar. Look at the difference. Whether this difference is big or not. Right? But we cannot tell whether it's big or not without considering how the variation of X bar. So what is the variance of X bar? If sigma is known, it is sigma over root n. All right? So this will be our test statistics. Next, I make a decision. I have to define my decision rule. So this is not good enough. I have to specify what is the critical values. All right? So I need to know the distribution of this one. So what is the distribution of this one? This one will be normally distributed with mean 0 and variance 1 if you have 1 and 2 conditions. And this will be approximately normal if you don't have 1, but you have 2 and 3. All right? You don't need the underlying distribution if your sample size is big. All right? So now I have the test statistics and I know the distribution. Then you ask yourself, what is the critical value, or how to define my critical region? All right? Now this is a little bit more complicated. We have 3 scenarios. One is a 2-side test, that is testing this one. All right? Oh, so then, now this is X bar, normally distributed, or approximately normally distributed. And under the null hypothesis, I have to stress that, under the null hypothesis. So therefore, this mu will be replaced by mu naught. Under the null hypothesis, X bar suppose follow this distribution. Under the null hypothesis. Because everything is assuming the null hypothesis is true. So we work on the X naught So H naught means mu equal mu naught. So under the null hypothesis, X bar behaves like that. All right? So now we talk about critical value approach. So I will decide on X bar, all right? If it is within this two bound, X1 bar and X2 bar. These are two numbers. We'll figure out what these two numbers are. Then I will accept it. So in other words, if X bar is greater than X2 bar or X bar is less than X1 bar, then my decision is rejecting the null hypothesis. So in other words, this is my X bar, this is my X2, this is my X1. Whenever it's here, when X bar is here, I accept it. Right? So the rest, I will reject it. So this part and this part, these two parts, is the critical region or rejection region. All right. So how to determine X1 bar and X2 bar? These two numbers. All right. So we need to know the distribution for X bar under the null hypothesis. All right. So here it is. So X1 bar and X2 bar are two numbers. So this is what I just said. All right. So now, in order to know what this X1 bar and X2 bars are, I need to have this one. This is the test statistic, follow standard normal. Oh, we know that between this minus Z alpha and Z alpha over 2, all right, between these two numbers, the probability is 1 minus alpha. Therefore, over this and over this part, the probability falls in this part and this part is alpha. All right? So, looks familiar, right? In the confidence level, we have something similar, but this is mu. But now we put it as mu naught. Then what we're supposed to do? Remember, I want to find the probability of X bar less than X1 bar, X2 bar is equal to 1 minus alpha. So this time, the work or the mathematics, the objective is to put X bar as one end of the inequality. There are two inequalities here, 1 and 2. Two inequalities here. All right? I try to rearrange it so that X bar is at one end of the inequality. All right? So you just multiply this to both. Do I have to change the inequality, the direction of the inequality? If I multiply by sigma over root n? Or in other words, is sigma over root n positive? Can it be negative? Cannot be negative, right? Sigma is a positive number, square root n is a positive number, so we multiply a positive number. Then you just rearrange it, so I got this. So my X1 bar is this. My X2 bar is this. All right. All right. So it's very straightforward. I know mu naught is under the null hypothesis. I know sigma because it's given. We assume that we know sigma. We also know the sample size, and we can get this one. This one, right, is published, so I can compute these numbers. All right. So my decision rule is that, okay, where X bar is greater than this number, I reject. Or when X bar is less than this number, I reject. Because when X bar falls within these two numbers, I do not reject. All right. So here's my decision rule is that, all right, I will reject when X bar is between X1 bar and X2 bar. But I can standardize it so that I know this is a standard normal between these two numbers is 1 minus alpha. So usually our critical region is stated in terms of some random variable which we know the distribution. All right. What I'm saying is that we know x bar is normal mu sigma square over root n. We also know that this one is standard normal. So under the null hypothesis, you just replace this by mu naught, replace this by mu naught. All right. So we would prefer to make our decision rule based on this. All right. So that once you compute the test statistic, which is this one, using this formula, I compare with two numbers that I can obtain from the standard normal distribution. All right. So, like for example, if sigma is not known, then what is the distribution of x bar? If sigma is unknown. Okay, I don't know, but I know this one. Under the null hypothesis, this one follows a t distribution. So in other words, I will not express it as x bar between these two numbers, but to express it in terms of this, which is our all these test statistics, x bar minus mu naught over s over root n. And I know the behavior of this test statistic. It follows a t distribution. All right. Okay, here's an example. Sorry, I have to finish this example. So we have breaking strength with 35 kilo and standard deviation is 1.5. So sigma is 1.5. All right. And we want to determine if this new machines with a big breaking strength of 35. That means we want to know whether mu equal to 35. So we take a random sample of 49 and the x bar is 34.5. All right. Can I just say that mu cannot be 35 because I got 34.5? Can I do that? Hey, this number is different from 35. So, sorry, mu is not 35. Can I do that? Why not? Mu equal to 35 is fixed. Your 34.5 is a realization of random variable, right? So just like toss a coin, you can have head, you can have a tail as a realization. So this time, this sample gives you an x bar equal to 34.5. Maybe another sample will give you another value. All right? A third sample will give another value. So you cannot, based on this 34.5 different from 35 and conclude that mu is not 35. No. So we have to do, so it asks, is there evidence that the machine is not meeting the specification? Not meeting the specification. So we are looking at whether mu equal to 35 or mu not equal or bigger or less than 35. Not meeting the specification. It can be bigger than 35, can be smaller than 35. All right. So this is the one. All right. So we want to find out whether this have a different mean strength. All right. All right. It's important that you have to specify what do you mean by mu. You cannot just write down h naught mu equal to 35 without saying what mu is. Mu is the mean breaking strength of the cloth manufactured by new machine. Okay? I try to break it into steps, but it helps you to understand the process. So this is the hypothesis, and we set alpha equal to 0.05. If it's not stay in the question, you pick up your significance level. Then sigma known, the test statistic is this one. Remember, this is the mu under the null hypothesis. All right? So the decision rule is the critical region is whenever the observed test statistics value is less than minus 1.96 or bigger than 1.96. Standard normal, 1.96 minus 1.96. If it's here, or if it's here, we reject the null hypothesis. And the chance of falling here or falling here, okay, the chance is about 5%. 5%. So where that is just replace this by the realization or from the data. So we compute it, and the value is minus 2.33, which is falling in the critical region because it's less than, this number is less than minus 1.96, right? Minus 1.96, 1.96. So this is minus 2.33. It's here. So it falls in the critical region. The critical regions have two parts. All right, so it falls in the critical region, so we make a decision. The decision is reject the null hypothesis. All right, so here is the idea. All right, 1.96 minus 1.96, reject the null hypothesis, and this one we do not reject. And since minus 2.33 is somewhere here, falls in the critical region, so we reject the null hypothesis. All right. Okay, I think I stopped here. All right, so we'll continue for the rest of the chapter next Tuesday.